Hey guys, welcome to Science 3.5. Make sure you have out your books because really I'm going to go over a lot of information today to help you understand this concept. I know that this chapter is very technical, and thank you for your patience for when I wasn't here and didn't have my book to help you guys, but now I've been able to study through this section and kind of give you some guidance so you don't feel like it's just like a ton of new information that you've never heard of before and you're trying to keep up with everything, okay? Especially since sometimes this book is, it's not written super great, but it's because it's hard to write a science book, to be honest with you. So anyway, so here we go with the video. These are the equations. You don't actually need to write these down or anything. This is just how I'm going to refer to them. They are all in your book, so you can highlight them or whatever. It's probably going to be, it's up to you and your style if it's going to be easier for you to write all these down. I feel like I would kind of get lost about what they were. It's better that they're in the context of the book. You can highlight them and stuff like that. These books are going to be used again, you guys, so like don't munchar them completely, but if you need to highlight an equation or something like that to help you find it later on, that's perfectly fine. Okay, we're not going to go over the entire section today, obviously. It's very long. We're going to do half and half, so half today and half on the next day that you have science class, which might be tomorrow, I think. So anyway, so let's get started with this. Also, I'm going to pop in like a 2-minute video to explain one concept because it's not explained at all in the book well, and it's explained really well with graphics and stuff like that in this 2-minute video. So I'll stick that in when it's time. Okay, so go over to page 71. So we can start to go over, remember what you're gonna do, you're gonna take notes on the concepts that I tell you now, not just on the whole thing, just on the concepts that I tell you. And what you also need to do for today is, you're not gonna have questions, obviously, because you're not gonna be to the end of it. You'll take the notes that I tell you and do the practice, okay? On page 73, practice 3.5a. What you'll do is you'll do it today, and then you will, check it with me tomorrow, okay? Because I'll give you the answers in tomorrow's video. Okay, so we're talking about simple machines. And it's kind of cute. It's gonna clarify, you know, we think of machines, you guys, as like the actual, like the equipment that people use, you know, to like construct and different stuff like that. But honestly, they say right here, a machine is a device for doing work. So a machine doesn't have to be electrical. Okay, a machine doesn't have to have like a motor or anything like that. It's just anything that's gonna help you do work. Like for example, if you look at page number 72, figure 3.33, the pulley that the guy is pulling on, that's a machine. Okay, it's a manual machine, but it's still a machine. So the very first concept that you're gonna look for 3 sentences on is, so you can make sure you write it down, simple machines versus modern device machines, with examples, okay? So you might need to go like kind of through the section before you find some examples of simple machines and stuff like that, but all the information is there. Okay, so 3 sentences, simple machines versus modern device machines with examples, okay? So if you look at if you're still looking at page 71, you're gonna be talking about mechanical advantage. What that means is that machines are there to help you do the work. So instead of you trying to pick up a heavy item and move it somewhere, you're gonna let the machine pick up the heavy item and move it somewhere, okay? So in that case, the machine is doing some of the work for you. The equation for work you're gonna see in your lesson on page 71. Work equals force times distance, okay? So if a machine is gonna be helping you do the work, that means that you yourself are gonna have to do less work, okay? Force times distance equals work. So if you're looking at a machine helping you do the work, then you're gonna be the one putting in the work with the machine, and then that is gonna produce an outward work. So there's an input work and an output work. And if you look at page 72, what they say basically is that work input in a perfect world should always equal work output, meaning whatever force you're gonna put in, that same amount of force and distance should come out, okay? So, look at the pulley. Look at the image right here, right? Look what it's trying to do. You're trying to pick up an 1,000 Newton box, okay? and you're gonna move the 1,000 Newton box 0.3 meters off the ground, okay? That is the work output that you want, okay? That's the proposito. You need to take it 1,000 Newton box, because remember, Newton is a unit of weight used in science. So you're trying to, let's put it here on the board. Your output that you want is 1,000 Newtons. That's your force, right? Times your distance, which is 0.3 meters, okay? Your work input needs to equal that for a perfect world. And you'll understand why I keep saying for a perfect world in a second. So, what are you gonna need to do with this machine? If it was just you working by yourself, you would have to pick up 1,000 Newton force and move it 0.3 meters. But in this case, you don't have to do that. In this case, you can use a pulley and only pull down on a 250 Newton force. Now, what do you think is easier? Picking up 1,000 Newtons or pulling down 250 Newtons? It's easier to pull down with 250 Newtons. That's the point of a machine, is that instead of you trying to do this, you can do just this. But here's what you need to understand. In order for the equation to balance out, that means that you're gonna have to pull a longer distance than 0.3, okay? So again, let me resumir all that. If you're going to use a machine to help you do less force to pick up or move an object, you're going to have to do that less force for a longer distance, always. Always, okay? So we set up our equation like this. F times D equals F times D. So 250 D equals 1,000 times 0.3, okay? So then we solve for what is D? 1,000 times 0.3 divided by 250, 1.2. So now you're gonna have to pull down on that rope in the pulley 1.2 meters down just to pick up the box of 0.3 meters, okay? Your distance is always going to be greater to do less force, which is fine because it's easier to go a longer distance than to go a bigger force, okay? So that's what they're gonna be talking about in that one. So you need to do for your second concept 4 sentences on mechanical advantage. If you look past that equation that I just explained, look what it says on this paragraph right here. One measure of how much help a machine provides is its mechanical advantage. That makes sense. There should be an advantage for using a machine, right? That's what it's saying. The mechanical advantage is the number of times a machine multiplies the input. So if you have, look what it says, if a machine with a mechanical advantage of 4 means that that machine helps you do 1/4 of the work because it's quadrupling the force by 4. Like this one right here. You only have to do 250 Newtons of force to get 1,000, right? 250 times 4 equals 1,000. So your mechanical advantage is 4. It is doing 4 times the work for you. That's the advantage of using a machine, okay? So how do you find mechanical advantage? It's right here. Ideal mechanical advantage equals input distance over output distance, okay? So input distance was 1.2, output distance is 0.3, and when you do 1.2 divided by 0.3, what are you gonna get? 4. So your mechanical advantage of this machine is 4 because it does 4 times the amount of work for you. Okay, now another concept you're going to have to do is the friction's effect on mechanical advantage. Okay, the friction's effect on mechanical advantage. And what is that? Look what it says on page 72. Page 72. In friction and machines. Unfortunately, the world is not ideal. So this is your ideal. This is your perfect mechanical advantage. All you have to do is do input distance equals divided by output distance. However, there's something called friction in the world. That it's not actually true that the work that you put in is the work that you get out. There's gonna be a loss of energy. There's gonna be a loss of work because some of your energy is gonna be lost from friction. Remember what friction is? It's that force that works against you to slow your energy down. So look what it says. Work output is always less than work input. The main culprit for this is friction. After some of the input work overcomes friction, what is left can actually be converted to work output. So look what it says. Although work is lost in the simple machine, energy is still conserved. It's just used somewhere else. Look what it says. The wasted work is merely converted into forms of energy, heat, sound, etc. Sometimes machines will give off heat. What is that giving off of heat sometimes? The loss of energy in its work. The law of conservation of energy says that energy is all the energy that is in the world right now is all the energy we're going to get. It just changes forms into heat, into sound, and different stuff like that. But you're going to lose it in the form of work, okay? What you put in, you're not always going to get out. So you have to account for that when it's not a real world. So look what it says in verse number, great. Look what it says on page number 73. In non-ideal conditions, the IMA cannot be used. Instead, the actual mechanical advantage is defined as the multiplication of the input force that a machine provides, so output force divided by input force. This is the real one. This is the fake world, which you remember scientists always find stuff in the fake world first, because that helps them see what is the actual effect of friction. What is the actual effect of air resistance, right? What is the actual effect of a negative force? So you first have to start out with what would it be perfectly if there wasn't that kind of stuff, and then figure out what that kind of stuff is doing to your science experiments, right? So you have AMA, actual mechanical advantage. So instead of doing input distance over output distance, you do output force over input force. Like, what do you actually get out of this machine, okay? So it says because the friction cannot be typically calculated, AMA cannot be determined from the machine itself. It must be determined from the forces, the actual result of what is going on. So look at example 3.12. A man who uses a simple machine to lift an 1,000 Newton box, like he was just doing on that other page, this time he exerts an input force of 275 newtons over 1.2 meters to lift the box. So what are you seeing here? You're seeing that honestly, when he goes to lift that box, it wasn't just 250 newtons that was required. It was 275 newtons that was required because there was friction in the air that was pushing down on the box, making it harder to pick up the box, okay? So in that case, when you divide the output force, which is going to be 1,000, divided by the input force, which was 275, not 250, okay, you all of a sudden have an AMA of 3.64, which means that really that machine's only doing 3.64 times the amount of work for you, not the full 4, because friction was working against you, okay? So then the last formula that they're going to talk about basically today is called efficiency. That's how well does the machine convert input work into output work, okay? So it's a lot like mechanical advantage. It's just a different way of looking at it. How efficient is this machine? Is it worth the advantage that you get, right? So now this is going to be work output divided by work input. Well, listen carefully, because in order for you to find efficiency, you first have to find work. So remember your equation that's disappearing. Work equals force times distance, right? So you first have to find that before you can find work output divided by work input. So let's look at example 3.13. Calculate the efficiency of the simple machine from example 3.12. So we want to do the efficiency of this one. Work output divided by work input. Let's first find the work output. Okay, the work output is going to be the force output. Well, the force output was 1,000, and the distance was 0.3. Okay, so that's going to be, again, 1,000 times 0.3, which is going to give you 300, right? Then the work input, the force times distance, the work input was 275 this time, times 1.2, which we get 330. Now you see the unit is joules, and maybe you learned this in another section, but joules is the unit for work, okay? It's a form of energy. So then you do work output divided by work input, so it's gonna be 300 divided by 330, okay? 300 divided by 330 is gonna give you 0.909, which is gonna convert into 0.91, which is 91%. That means that this machine is 91% efficient. And then you decide whether or not you like a machine that's 91% efficient, meaning that you're losing about 9% of your energy is basically what's happening, right? It's not 100% efficient, but maybe compared to another machine of a different marca, a different company and stuff like that, maybe that machine's 85% efficient, right? So you decide to go with a 91% efficient machine for your factory. Okay, so these are different things that you need to look at. And look what it says. That means that 9% is lost in overcoming friction. Okay, 9% of your work is lost by overcoming friction. So that information all right here is gonna set you up to be ready to answer these 4 questions in 3.5a. What you do need to understand though is look at number 2. It says a machine with an IMA. It's not true. A machine with an AMA. Change it to an AMA because they were using the wrong formula. You need to use this formula right here. You need to use the formula for AMA, not IMA, okay? So, you have, so far for your concepts, you need to do simple machines versus modern machines. The second one is explain, did I tell you that? Explain mechanical advantage. Number 3 is what is the friction's effect on mechanical advantage? Number 4 is what is the difference between IMA and AMA? Okay, what is the difference between IMA and AMA? 3 sentences on that one. Number 5 is what is efficiency? And number 6 is the lever classes 1, 2, 3 with examples. The lever, L-E-V-E-R, classes 1, 2, 3 with examples. And you're like, what in the world is that? Look at page 73. There are 6 simple machines. The lever, the wheel and axle, the pulley, the inclined plane, the wedge, and the screw. And you're like, I only know some of those words and I don't know the other ones, Miss Jessica. That's okay, because they're gonna start to go through them right now. The only one you're gonna learn about today is the lever. And that's where we're gonna stop. We're gonna stop right here. Right above the wheel and axle on page 75. But honestly, you guys, you don't even have to read this part right here. Page 74, you don't have to read that. Just watch the video I'm about to attach, okay? It's gonna explain the 3 types of classes of levers, okay? Class 1, class 2, class 3, and that's the last thing you need to do today, okay? Review again. Simple machines versus modern machines, 3 sentences. Mechanical advantage, 4 sentences. Friction's effect on mechanical advantage, 3 sentences. Difference of AMA versus IMA, 3 sentences. What is efficiency? 3 sentences. Make sure you do practice 3.5a and then do 4 sentences on what are the classes of levers, 1, 2, 3 with examples. There are examples in your book on the picture, so that will help you as well, but there are examples in the video too. Okay, thanks guys. Let me know if you have any questions.
Welcome to Moo Moo Math and Science and types of levers. A lever is a simple machine, and they're a basis of many tools in and around your house and work. The way levers work is that a force is applied at a point, and this moves the load at another point through a balance point called the fulcrum. It's the position of these 3 points, the force, the load, and the fulcrum, that distinguishes the type or class of lever. There are 3 classes of levers: first, second, and third class. With a first class lever, the fulcrum is in the middle, and the force is on one side, and the load is on the opposite side, much like this seesaw. Other examples include scissors. Here's the force, here's the fulcrum, and the load. And also pliers. Second class levers have the load between the force and the fulcrum. For example, with this wheelbarrow, here's the fulcrum, here's the force, and then here's the load. A nutcracker is an example, and also a stapler. A third class lever has the fulcrum on one end, the force in the middle, and the load at the end. For example, with this hockey stick. This rake is a third-class lever, and also a hammer. So there we go, 3 types of levers. Thanks for watching, and Moo Moo Math uploads a new math and science video every day. Please subscribe and share.